Hello, welcome to another wonderful episode of the New York City Category Theory Seminar. Today is April 26th, 2023, and we have Dusko Pavlovic, who's coming back. You spoke before, you spoke last year, and he's going to talk about program-closed categories. Take it away, Dusko.
So thank you so much for inviting me, Nozon. So I'm just gonna, let me see. Okay, so this is first, I don't know whether I should read this or this is where I say what I'm going to talk about. So first I'm going to say how are these program closed categories related with the usual closed Cartesian closed categories, so that take us from lambda abstraction to program abstraction, which is an important step. And then we kind of get in trouble. The theorem which I'm claiming is certainly unexpected by me, and it might be conceptually unexpected, but there is trouble of proving it, and we need to get from program evaluation to program execution in that categorical framework, which is a bit of trouble. So then I'm going to talk about that. And then we prove Cantor-Bernstein, well, actually, we proved it the way Cantor proved it and never really endorsed his method. So then I'm going to, in the end, maybe talk about the morals of all of that. So what is the theorem and what is the framework? So the Cartesian structure can be viewed as a family of natural bijections. Here they're x indexed, here they're x natural, and for every pair of objects A, B, we have one such natural bijection. And then when we have Cartesian structure, then Cartesian closed structure can also be viewed as AB indexed family of X natural bijections. And then we get to program closed structure, which is an AB indexed family of X natural surjections. So while in the previous case, we said that this covariant functor out of C into sets was representable by the exponent. Here we can't say that anything is representable because everything is quote unquote represented by the same object, which will play the role of programming language. But we come up with a very crazy claim that if we are given that this structure, the AB index family of X natural surjections, I will say in a minute what everything is. There is a tensor rather than Cartesian product now, and there is this dot which says that this category is Cartesian. So there is certain indexed family of natural surjections, and the claim is that with basic structure, which provides us with data services for this programming language, that this structure is unique up to isomorphism, that it is not a structure, but that it is a property of this monoidal category in which it is happening. So again, we have a covariant functor out of C into set. And what we are saying is that it can be that this covariant functor in its functor category can be covered in only one way. And I expect that people here will realize how crazy is this claim that if I give you a set and I say that there is just one surjection on that set, there's only one such set, the empty set. All other sets can be covered in more ways. Or if I give you a topological space and we say there's just one étale map on that topological space, it can only be covered by one local homeomorphism. There's not much of that topological space. It can also be empty, or it can be a single point with respect to local homeomorphisms. But there are not many situations in which a claim of this type might be true, especially in variable worlds such as worlds of free sheaves or covariant functors. Yet here it is true. So here's the formal theorem. It is true because it defines the notion of computability.
Dusko, can you go back 2 slides and tell us what P is? P is a set of programs, fine, but tell us how to read this. You have functions that
I give you a monoidal category C.
Right.
And I say that monoidal, I was going to spell it out in the theorem, but I can say it here as well. Okay. Every object is equipped with a comonoid. Okay? Right. Now, with respect to these comonoids, the comonoid homomorphisms form a Cartesian category, the largest Cartesian subcategory of this category. Okay? So now, there are home sets in this Cartesian category. They are the Cartesian, the total single-valued morphisms in the category C into this fixed object P. I just say there is a single object P such that for every pair AB, there's a natural surjection, natural in X of this type. So for every morphism, for every X-indexed family of morphisms from A to B, there is an X-indexed family of elements of P, which covers that morphism. And that will be the program for this computable morphism. In fact, the existence of such an X-indexed family will be the abstract characterization of the notion of computability. Okay,
so the A's are the inputs, the B's are the outputs, and what's X correspond to for computer scientists?
For computer scientists, X are parameters of your program. In addition to, so inputs you give to a computation when it runs. Before it starts running, you give your program some parameters, and X are these program parameters. They are not the input. So if I'm a payroll system, then X will tell me which month am I in, whether it's a 30-day month or 28-day month, or before I start calculating salaries. Okay. Or if I'm a pocket calculator, X will tell me which arithmetic operation I should apply to A to get B.
Okay, and A is a comonoid, means the inputs can be repeated and the inputs can be deleted.
Exactly. These comonoids are what I call the data services. And you can, for instance, think of the category C. I mean, in contrast with some other models, we can fit here quantum computer, where of course we can't copy or delete quantum data. So these copyable and deletable data would be the characterization of classical data in a quantum world. In the usual Cartesian world, we can copy or delete anything, but if we're in a computer, then we have side effects, then we have computation which may not terminate. So then it immediately isn't a Cartesian category anymore, as obviously everyone knows. So we need to take into account, on one hand, total single-valued morphisms, because if I have a parameterized family of programs, I better get an actual program when I enter a parameter. But if I have a computation and I enter the input, I might not get the output because the computation might diverge. So, our categorical framework needs to take care for such things, which is why we have to distinguish that we're drawing programs from this Cartesian category, and the X-indexed things are parameters. And for every parameter, we definitely get a program. But on the other hand, A inputs may or may not give B outputs, depending on whether the computation terminates or not.
Okay, so just one more question. So the programs live in the real world, and I'm sorry, yeah, the program and the input and output functions could be part of the quantum world.
Possibly of quantum world or non-deterministic world, or randomized world or DNA world. I mean, if you want to ask yourself, where are we concretely? Where are we with respect to the models? Then you can pick up your favorite programming language, Python,
Yeah.
And then this you can take this object P to be the set of expressions that don't even have to be well-formed expressions. They will be interpreted by Python, let's say, interpreter. Now, these interpreters some of the computations which they will interpret will be idempotent. Every native type in any programming language can be the type checking will give you an idempotent computation, and other idempotent computation will give you types. So you can take objects to be idempotents on your set of program expressions, and you will get a category of such types. The morphisms between them will be computations. What does it mean to be a computation? Well, there are computable functions between these types, and we will see that what being computable means. It means being programmable. So if to this story about data services and an interpreter, I add the requirement that my programs are well ordered, then there is at most up to isomorphism at most one programming language in my universe. That's my theorem.
I understand. Thank you.
Okay. Any more questions? It's a crazy theorem. I mean, I didn't expect that it would be true that we have just like, so if you think again, since I kind of diverted already, if you think of Cartesian closed categories as the standard core of every model, every extensional model of computation. So now here we're asking ourselves, what is the categorical model of intentional models of computation, including Church-Turing Thesis, including Turing machines, lambda calculi, and so on. And not only is this the categorical core of each such model, but the crazy and unexpected thing is that it is unique up to ISO. So here's the theorem. So you've got the symmetric monoid. Whenever I say monoidal, I mean here in this context symmetric monoidal category, and we even strictify it with a comonoid on every object. So this is my data services. And then with respect to these comonoids, intelligently, I didn't bring any tea or anything to lubricate my mouth. On each of these, for every type, we have the data services. We have a copying and deleting facility. And then we denote by this bullet the Cartesian subcategory of comonoid homomorphisms. So those are the computable functions to be thought of as computable functions which are total and single value. They are deterministic and they do terminate. Then any two indexed families of X natural surjections are isomorphic as soon as P0 and P1 are well ordered. So if we have two programming languages, we can construct a computable isomorphism between them. Computable isomorphism means it preserves the meaning, and the meaning it will be expressed by the representative of this surjection. Okay, So this is the
if your favorite programming language is Python and mine is Java, can't I say, won't there be 2 Java programs for every Python? I mean, why is it an isomorphism?
because it is invertible. Because in either Java or Python, I will construct for you a computable function which will translate your Java program into my Python program in such a way that it will have an inverse, which will get back out the Java program, which will execute precisely the same up to every execution step, which presumably for Java precisely means that it will have the identical bytecode. Of course, now it will be up to renaming of variables and parameters, and you can write it in different ways, and in Python's the indentations will not be the same, but the execution will be on the nose. And that is what we construct. And that is what we construct, crazy enough, by reading Cantor's proof of Cantor theorem.
I just say, in the regular world of compilers, I mean, they're not invertible. So, you take a C program and you compile it into assembler. There's more than one way to uncompile it.
Yes, absolutely. Compiler is not program evaluator. Compiler is a program optimizer. Compiler does more that, so if we read any interpreter specializer book, any book about program evaluation and specialization, then compilers do not subsume. Compiled languages are different from interpreted languages, and are different even from languages which are just executed or evaluated. Compilers do things with programs. Compilers are meta programming devices. I mean, compiler, the way I think about compiler is, if you think about the electrical network in your house, everything is reversible except the fuse box. Through the fuses, you can go one way, but you can't go back. And through compiler, you can go one way, but you can't go back. But if you separate out the program optimizations for interpreted programs, the categorical claim is true computationally on the nose. We can put next to each other the 2 interpreters, and they will be step for step. But you will see the construction. The construction requires that we go from interpreter to from evaluator, from interpreter to a state machine. We need to go to command. So let me show you what is interesting in the proof and why it happens. If you
Yeah, no, please, thank you. I'm sorry for the bother. I'm sorry for, now I get it straight. Now I understand why you're bringing in Cantor Bernstein, which is about showing isomorphism. Makes sense.
Yeah.
Excellent. Thank you. Please.
Okay, so why under the sky is this true? Why would there be one natural surjection to some functor? Well, again, going back, Cartesian products, it means that something is representable. There's a representing object. Cartesian closure, again, it means that some functor is representable. There's a representing object. Here, like I mentioned already, there is no representing object, but what we have here is a single instruction programming language. And in my book, it's called run. And what do you think the single instruction is called? It's called run. What does it do? It's running programs. If you want to think of the lambda calculus as a 2-instruction programming language, then this would be application. And what we are saying is that if we want to be serious about having a non-extensional model of computation, and non-extensional lambda calculus is not non-extensional model of computation because it is essentially extensional. Every non-extensional lambda model has an extensional retract. If we want to be genuinely non-extensional, to have Turing machines or arbitrary programming language as source of our models, then we have this one, then we have this single instruction. And well, okay, and now I'm going to go to the representative of this single instruction, which is the program evaluator. And I hope later I say there is a chapter in the book which shows how all of the standard program instructions are derived from this single instruction. So there's a chapter where in like, I don't know, it doesn't take too long, maybe 25 pages, we go, here's how from this instruction we derive native natural numbers. And for native natural numbers, here's how we derive native primitive recursion and native minimization and native while loop and so on. So what this, well, we all remember, naturality means polymorphism. And in this case, naturality means that we will have a representing, so for every AB, the image of identity will represent the entire natural transformation run AB. So I guess for this audience, I don't need to run through this naturality. So if we have the program evaluator is the image of the identity on P along run P, so that for any program, any X-indexed program G, the image along run will be its evaluation along the image of the identity, which I denote with Kleene's curly brackets. This is the program evaluator. I think, yes. So here's how we get into business of proving this. So first of all, such natural transformations are completely determined and in one-to-one correspondence with program evaluators, which are the morphisms from, in this case, from P times A to B. Here is the program evaluator. And what the statement that this natural transformation is surjective says is that for every morphism from X tensor A to B, there is a program, an X-indexed program, capital G, such that when I pre-compose my program evaluator, when I evaluate the program G, the program capital G, I will get the computation little g. And the computability in my category is, in a sense, defined by the existence of programs. So this surjectiveness tells us that we have that every morphism is programmable. Okay, and this is but note that the claim is indexed along x's. In principle, any type can be taken to be the indexing type. So I can, when you give me a morphism G, I can take both X and A to be inputs, and I can find a fixed program. Or I can take both X and A to be parameters, and I can take an X tensor A parameterized program, which will then be run and seek no inputs. So that first of all, so this program evaluator operation, the single operation, is the single instruction of the single instruction programming language. And chapter, what is it, 4 in my book, which will appear, I think it looks like maybe even next month in Springer Nature. They're really rushing with it, but I'm allowed to distribute draft for free. So if anyone wants to see it, I'll be very delighted to send a copy. In chapter 4, we just derive everything from this one instruction. So, how that works. So first of all, like I just said, you can take your function, you can take both x and a to be inputs, and you can have a fixed program. Or you can take, so forget this gamma, you can take your computation to be the program evaluator, which takes two inputs, x and a. And then the axiom says that there is an x-indexed family of programs, which is the partial evaluator, such that if we execute that, if we evaluate that program by the program evaluator of type A only, we will get the program evaluator with input x tensor A. Okay, so that way the axiom boils down to having universal evaluators for fixed programs. So if someone gives me a function, I can find a fixed program for that function. And moreover, if my function requires several arguments, several inputs, I can partially evaluate on those that I have, and the partial evaluator, which we denote here with square brackets for algebra, will then output a program which will wait for the missing inputs. So this is like the function abstraction before. So there are kind of two ways to define the what I call monoidal computer structure. One is with this axiom that for every computation with inputs x and a, there is an x-indexed program. So these bullets mean that this particular box denoting a morphism in the string diagram is total and single value, that it is in the Cartesian category. So this is the program which lives in the Cartesian category. So there's an indexed program which, when evaluated, gives that function. But I can also say, I can seek here a program indexed by both x and a, or a program indexed by nothing, by the unit type, and then the program evaluator will eat inputs of both types x and a. And then we can, so the first thing that we can do is partially evaluate things and slice these inputs. And here's an example of slicing. So for any function, on one hand, I can have an x-indexed program, or I can have a constant program, and that constant program I can partially evaluate if needed, and then I will have the x-indexed program. And at this level, then we can also prove that these surjections, they are always non-trivial. There are always infinitely many programs for every either the computer, either the program-closed category is trivial, and we can prove that in the type of Booleans which we can derive true is equal false and everything, every two morphisms are equal. If it is non-trivial, then there are infinitely many programs for every computation. Already at this level, we can prove that. And then some things become so why are we using these pictures? Because some things become much simpler. So here's the fundamental theorem of computation, which I'm calling it that this is called deprecatingly by Kleene's second recursion theorem. It says that if you have a computation which takes programs as inputs, then it has a fixed point, namely there's a program which, if you run that computation on that program, you get the same thing as if you run that computation. Okay? So no, if you run that program, I said it the other way around. If there is a computation which takes programs as inputs, then there is a program such that the value of that computation on this program is equal to running to the outputs of running that program. And here's the construction of that. How do we construct that is known as Kleene fixed point? And everything is can be programmed using Kleene fixed points. This is our omega constructor from lambda calculus. How do we construct Kleene fixed point? Well, we pre-compose the given, so I'm now constructing the Kleene fixed point for an arbitrary computation G. Well, what do I do is I pre-compose this computation G on the input, which is of type programming language. I pre-compose it with a partial evaluator, which partially evaluates programs on themselves. So what this G pre-composed with partial evaluator is doing is it inputs a program, partially evaluates it on itself, and then feeds it as the input to G, and G works on it. Okay? So now, by the assumption, we know that everything has a program, and if G is a programmable, its version pre-composed with partial evaluator is also programmable. So let's now call a program, one of infinitely many programs for this computation. Let's call it big G. Okay, so first of all, with input big G here, this is we define big G as the program for computation little g pre-composed with partial evaluator evaluated on itself. This is a mouthful in English, and it's also a reasonable mouthful in any programming language, but it's a simple picture. It's this picture. Okay, and now if I give this G as input to itself, okay, I have this program evaluator which runs G to get little g with partial evaluator, and moreover, I add big G as the input which it seeks as the input here. And since I'm using 2 copies of big G, I can just as well use 1 copy and then copy it. And now if I partially evaluate the program, this program evaluation, if I partially evaluate on the first argument, here's the partial evaluator, and G partially evaluated on itself is the Kleene fixed point. Now, you know, if you have read Kleene's proof of this, was in the original paper was, I think, 2 pages, and you know, the Freddy, it's like a page. And then when Dusko is talking about it, it's 15 pages and completely incomprehensible. But if you look at this picture, you know, then you may even understand what Dusko meant to say. So, you know, we gain things by representing them as string diagrams. Okay, so now we get in the business of proving the theorem by observing that if every function is programmable, then if I have 2 programming languages, the interpreter of each of these programming languages will be programmable in the other one. So there will be, if I have programming languages P0 and P1, then there will be a P0 parameterized program, which when fed to the P1 interpreter will behave like P0 interpreter, and the other way around. And this is your regular, you know, Church-Turing reducibility of models of computation, or Turing completeness of any programming language which you have. If we know that Python is a Turing complete language, then we know that we can write Java interpreter and Java compiler if needed in Python, and that we can do the same for Python in Java. But you know, then if we reduce Java to Python and Python to Java, then we can compose these 2 reductions, and the reduction of Java to itself will be nothing like Java, but it will be very, very clumsy. And if we reduce it twice, it will be even clumsier, and so on. So these reductions, we know that reduction of Turing machines to lambda calculus exists, but it's as clumsy as it gets, and vice versa. So we get for cheap reducibility, computable reductions between the evaluators, but our claim is that there are computable isomorphisms, that we can find these phi's to be invertible, that we can make them invertible. So how do we do that? I don't know how to do that. It's possible that there's a clever way to do it on program evaluators. I don't know how to do it on program evaluators, but when we ask ourselves, so I have this monoidal category, and I have this one object and one morphism, and I'm claiming that it does all the job of everything. And I theorize, like in Python can be reduced to untyped lambda calculus. And that's a quirky fact, but how useful is it? And then when you ask yourself, but here I can form this category from an actual programming language, and I'll have this category where this object will be all the expressions in this programming language, and this actual interpreter will be an actual morphism here, and I say that I can interpret all these things, and all these functions which I'm programming are the real morphisms. So then I ask myself, so what does actual program execution look like in this category? And then you start, then instead of having these parametrized families of programs, you start looking at state machines. Instead of looking at computable functions which are indexed over some type, you start looking at computational processes which are stateful, which, a computational process has some state from which begins, and at each step of execution, it updates that state. So here on the left-hand side, I have the re-indexing of one parametrized function to another parametrized function. On the right-hand side, I have two computational processes and so if you think of this machine, if you think of this Q as a state machine where X are the states and A and B are the inputs and outputs. So this is, your regular Mealy machine. If you think of these computational processes as Mealy machines, then these re-indexings are simulations of Mealy machines. So what it says, what this S function does is that whenever the process R makes a step out of whenever Q makes a step out of X, then R will be able to make a step out of Sx into R of Sx, which will be the simulation of the next state of Q. So whenever Q makes a step out of some state, R will make a step out of the corresponding state into a state corresponding to the next state of S. In other words, R simulates S. So as far as Q goes as a process from state to state, R will be able to go from corresponding state to corresponding state, and it will be producing the same outputs on the same inputs. Okay, so now if you don't look at just parametrized functions, but if we look at computable state machines, then we're in the business, because then we can do much more. In addition to saying that that for every function I have a program which will execute that function on given parameters, what I'm having here is that for every computational process which updates its own states, it has input state and input value, and it outputs some value and updates its state. Now, we can prove that in this framework of program-closed category, the program evaluator gives us universal simulator, which will have programs which will predict the state update. In other words, we have here the universal simulator which runs some program, and it outputs the updated state, namely such state which on the next state of the computational process which is being executed, that next state will the simulation will map into the corresponding state of the universal simulator, will be predicted, anticipated by the universal program execution. So in terms of, if you think of your Mealy machines as coalgebras, what we're saying here is that programming language is the state space of the weakly final coalgebra for all functors that can be represented in this computable universe. So we have a universal universal coalgebra, if you like. So here's how. So here is how the this universal. Here's how we prove that the program evaluator plays the role of the universal coalgebra. What we do is that we apply the fundamental theorem of computation, the second recursion theorem, on so we want to find the simulator by programs of a computational process Q. In order to do that, we post-compose the computational process Q with the partial evaluator. Okay? Now, by the fundamental theorem, that computation, the post-composition of Q with partial evaluator, has a fixed point, which, when we execute it, we'll get that same thing. Now, that fixed point, which occurs here on the left, on the right-hand side, if I partially evaluate on it, I will then get this this X-index program Q, which is the simulation. So in other words, programming languages are universal simulators. I mean, you know, formally, it hasn't been derived that I know anywhere, but intuitively, if you're thinking about imperative programming languages, that is the whole idea, that the programming language is the simulator of all the possible stateful processes that we can specify in, I don't know, BASIC, or, I mean, Java is also, in a sense, an imperative programming language, among other things. So the programming language is a universal state space. It follows just directly from the fundamental theorem, and the proof is not significantly more complicated. It's also just 4 equations. So it carries weakly final coalgebras for all functors. When I say all functors, it means all functors which are specifiable, computable within this category, in any case, for all input-output types. Okay, so now we're in a slightly better situation, that now we have two. So now programming language is a universal simulator. So if I have 2 of them, they will be simulating each other. So now I have stateful reductions. My 2 programming languages must simulate each other. So whenever one of them makes an execution step, the other one will be able to make an execution step or more. So the rest of the job will be, how do we make it injective, and how do we then use these injections to get an isomorphism? And that is where it gets kind of nasty. That is where you said the chapter 7 with state machines gets complicated. So in any case, now what I have is I have 2 programming languages, P0 and P1. Okay, and I have 2 interpreters which are updating the program expression. So in other words, you can think of them as execution engines. Each of them takes, I have no idea about the time. Okay. No, I know.
It's about 10 to 8.
Yes, I'll manage. I'll manage.
Okay.
I'll manage to make the point within the next 10 minutes, I think.
Okay.
All right, so we have so far derived that we can construct for any two programming languages in our program-closed category. So if we have two of those surjections, we know how we can construct for the corresponding program evaluators, because there are also program execution engines which update programs. We know how to construct, from the universality statement it follows, we know how to construct simulators. So now how can we make these simulators faithful? And I thought that is where it would stop. But actually, there are two steps. If you do your coalgebra, you will figure out how to do the lossless program executions. So these simulations, which will where the state machines that we are simulating will be embedded into the programming language. So if any command, any instruction is repeated, the execution will be sent back to that very command. In other words, we will know how to make our programming language imperative, so that if we have a state machine, that state machine will be an actual execution, will be executed as an actual execution of an actual imperative program. In other words, instructions are commands. So when we're executing, the repeated command is just that command in the program code, and I'm sent to the same place in the program. So the first step will be to encode in the signature, in the monoidal signature of program-closed category, the lossless program executions, where these interpretations, where these the simulations of programming language in each other are injective and monotone with respect to the well ordering of programming language. So now this well ordering is the crucial step, and we all know, if as long as we are in digital computers, every programming language is well ordered, because everything inside is a bit string, and every 2-bit string are comparable, and some are bigger, some are smaller. Behind the screen, there's actually the stepping stone into Kolmogorov complexity, because this comparability of programs and well ordering of programs, the assumption that there must be the simplest program for every computation, it's the fundamental step. And it looked like, where is this well ordering coming from? Well, it's coming from the fact that everything that we're looking at is language based, and languages are these well ordered things where everything has a beginning. So the first step will be to develop lossless program executions, and the second step will then be to just execute the well-ordered Cantor-Bernstein theorem. And well-ordered Cantor-Bernstein theorem is just simply the Cantor theorem, which he never even wrote down because he was intimidated by Dedekind away from it, as we can read in Emmy Noether's publication of their correspondence. So that's a little bit dramatic moment, but it works for this theorem. So let's make these last two steps. We define imperative programs to be those that satisfy these two conditions. They are kind of more succinct to write down. So in this ordinary diagram. So commanded are padded states. This projection doubles the programming language, and then projects. Every type is the retract of the programming language, and then projects one of the two copies of the programming language to X as a retraction, and keeps the other half for padding, for passing arbitrary states, which is how imperative evaluation works. And the second diagram says yeah, I mean, everything has a simulation. Every imperative state machine has a simulation, but that simulation splits along this projection. So in other words, there is padding. So now this isomorphism theorem is a version well, there are two closely related theorems which are both also referring to Cantor-Bernstein. One is Myhill's isomorphism theorem, and the other one is Hartley-Rogers isomorphism theorem, that there's isomorphism between any two program enumerations, and crucial role in both of these. Both of these are very low level on the level of Turing machines and Kleene enumerations, but the crucial role in each of them plays the padding. And this padding is actually hiding that they are transitioning using Kleene enumerations onto imperative programming, and that now things are being simulated. But the way we all owe it to Cantor, I will point to in a minute. So here is, I don't know whether it makes sense trying to talk through this construction. Here's the construction. Here's the proof of the theorem that every computation has an imperative program which will faithfully, which displays the code in a non-repetitive way, so that any loop is a loop over a command. And here is some bookkeeping of the padding used by pairing and by partial evaluation. But I'm kind of worrying that this might be an example where a picture is maybe worth than at least an English sentence produced by a foreigner like me. So I'll spare you of my English sentence for this, but in any case, for an arbitrary computation, the imperative program is constructed by combining partial evaluation and categorical padding, which also arises from computability. So this brings us, with respect to that original natural transformation, brings us into a funny situation, which is beyond my intuition. Usually, when you have state machines, for every state machine, a state machine induces a simulation, which is a morphism into the final coalgebra. And here we have, for imperative programs, we have actually brought ourselves in the situation where for every simulation there's a state machine. That is the nature of imperative execution. So that's kind of the derivative of that. Well-ordered Cantor-Bernstein. So how do we say total order? I mean, I'm just displaying that this is how probably everyone would describe total order. I'm just drawing it in a monoidal category. Well, actually, here we're using Cartesian structure, copying. In any case, on every type, here we say that the order which we are given on programs is reflexive. Here we say that it is transitive. Here we say that it is symmetric. Here we say that it is antisymmetric, that it is partial order rather than pre-order. And here we say that it is total, that of two things, either one must be greater than the other one. And then well-ordering is encoded for every decidable predicate, there is a minimum. For every non-empty decidable predicate, and here I'm cheating by writing in the non-emptiness by the name, but the non-emptiness is assured as a property of the decidable predicate. So there's the minimum, which is smaller than everything, and it satisfies the predicate. And no, here we say that it is smaller than anything that satisfies the predicate, and here we say that it satisfies the predicate. Well, using the well-ordering, we first have monotone programming. So we can first prove that for for any given computation, we can find a program larger than arbitrary given value. So that is, we can sufficiently pad programs to and the infinite set of programs for every computation is unbounded in this well order. And from that, we can prove that we show that our basic program constructions are inflationary, that they increase, they are greater than each of the components. And from that, we can derive that our simulations can be derived, since they are derived by these program constructions, can be made injective, monotone, and inflationary. And then we go to 19th century, and we find a version of what was later reconstructed by Kleene, but without the well order. We find how Cantor originally, when he asserted the Cantor theorem in correspondence with Dedekind, how he was constructing it, assuming that the world is well ordered. So he was assuming that every set has an order type, which means since these two functions which are going, these two injections which are going two ways, since they're monotone and inflationary, they are sending each element to something that is greater to it. If we go there and back, we get something greater. If we go there and back, we get something greater. So we have these alternating, for every element, we can find his alternating orbit through two sets. And then from well ordering, he found that every alternating orbit must have a minimum. And then if that minimum falls on one side, we use one of the two injective functions to map that element up its orbit. If it falls on the other side, we use the other one, so that our bijection, from our two injections of two monotone injections of two monotone injective simulations of two programming language in each other, we are deriving two parts of an isomorphism like this. So if the minimum, so if the minimum falls on one side, these underlinings are the inverse components. We have injections, and if it is in the image, as theta 0 says, then we go back along theta 1, 0. Otherwise, we go forward, and so on. And that gives us the isomorphism. So
isn't Cantor-Bernstein, isn't it a transfinite argument someplace? I mean, you drew out the transfinite argument.
Well, he used a well ordering, right? So in there
So you don't need it, or it's stated and it's not used, or I mean, that was the reason why it was so radical, because it was a transfinite.
Well, yes and no. There is, for instance, a big confusion. You can't convince people that the Turing machine doesn't have an infinite tape.
Right.
Turing was very careful to say that the tape is unbounded. Computer never runs infinite, anything. Whenever you stop it, it has finite history. The tape is bounded, but it's a little bit like cloud. You can always extend more memory. Here, we never need to go into the infinity. And there is the cogent prose argument in a letter to Dedekind, which states what I just spelled out. It goes as far as needed, and it is not tractable in the sense that without special decidability proof, in principle, with Cantor's constructions, you don't know that they will terminate. But all that Cantor is doing is he says, I count, and I count as far as I can. And then what does it mean to be transfinite? It's again, he says, and now suppose that I have counted forever, and now at the end of forever, I start counting again. So transfiniteness is a bunch of als ob Kantian arguments under the assumption of possibility. So if we assume that I have ran infinitely long, then my normal form will give me the next coefficient in my ordinal expansion. So similarly here, we know that we have proved that these two predicates are decidable. So we know that the counting will stop at a finite point, and there is nothing transfinite here. The introduction of, so that is, maybe let me go here. I'm leading in the conclusion that the reason why this final section is called moral is that really there's moral of it, and it concerns Cantor and your question. So the Church-Turing Thesis says that there are all of these different models of computation, and that for any two of them we can find reductions from one to the other. So where does it leave us with respect to the notion of computability? Is that, you know, computability is some kind of invisible ether in which all these models are drenched, and, you know, somehow it stays behind them. And we can never capture computability itself, but we can only capture its avatars, which are reducible to each other. While actually, you know, in real life, what it means for a function to be computable is that it is programmable. You know, computability is just programmability, and it's programmable in any of these languages. And, you know, there is of course the big world of different languages, like they are all different natural languages. People on Earth speak many languages, but they all speak languages which are based on the same capability of speech. You know, the fact that we speak different languages doesn't mean that there is ether of speeches. It just means that things have diversified in certain ways, but there is the underlying structure, there's the capability of all of the languages. And we needed these machines to tell us that there's a uniform capability which binds all capabilities of speech, like there's the uniform capability which binds all, I don't know, birds and poets, you know. So all of these languages have, and all models of computation have this same underlying structure, which maybe clumsily I have expressed in this way. Maybe there are better ways to express it, but the claim is that whichever presentation, mathematical presentation one might take, there is the mathematical structure, canonical mathematical structure, which a monoidal category can have, which makes it computable. And there's, you know, there are no degrees of freedom aside of these isomorphisms there. You know, so I mean, I just said what the message of this. There's a Babylon of programming languages, but each of them induces a program-closed category. You know, so the invisible ether is this monoidal structure. And you can, I described it in the beginning. P is the program expressions, A are definable data types, and morphisms are programmable functions. And, you know, computable is the sticker which we put for programmable. And, you know, Cantor spelled out, you know, this very difficult construction which I spelled out, you know, in the sweat of my face, was spelled out by Cantor, what is it, 150 years ago, as a computation before the notion of computability, and before even the problem of computability was, and decidability was even stated by Hilbert and solved by Gödel and Turing. You know, why? Because Cantor started counting things, and he said, oh, you know, how can I compare these things by counting them? And first he invented this thing which we attribute to category theory, to look at things modulo bijection, modulo isomorphism. And then he invented these constructive arguments based on well ordering. If I push it up, and then if I know that it's well ordered, I know that I can begin. If I know that I can begin, I can constructively define it forever, and they are in one-to-one correspondence. And then Dedekind said, yeah, but what you're really saying is that real numbers can be well ordered, you know. And if you look at the real line honestly, real numbers can be well ordered. And, you know, Kronecker has already told you that real numbers can be well ordered, and that's ridiculous what you're saying. So I would really not go for this proof by well ordering. And Cantor spent the rest of his life struggling, even trying to prove this well ordering principle, until, you know, Zermelo said, well, no, there's no well ordering. We can just hide the well ordering, and when we need to well order things, we can say, oh, we can choose them in some arbitrary way. And, you know, and we all know how it all goes. And it took Turing to say, Turing's paper is about real numbers and about programming real numbers, and the codes for programs for real numbers, which Turing is presenting in his paper, are ordering all of the computable real numbers. And those that are not computable, we can't get to them. And of course, they're in disorder because we can't get to them. You know, and then Kolmogorov said, and moreover, by ordering these real numbers, we can also order the amount of content in which real number has. And then, you know, then there's this abstract real number, which Chaitin said contains all the wisdom of the universe. So the morals is that all these people, you know, have noticed this thing, this morality of well ordering and constructiveness, and have been pushed out of it. You know, one into an asylum, the other because, you know, he knew too. Anyway, I mean, in any case, the morals of it is that understanding these things doesn't get us very far, because both of these guys have said these things a long time ago, and we are still, you know, living in this Babylon. And so if anyone wants my book, please ask. I'm dying to have some readers, but I will totally understand if there are no readers. Thank you.
Thank you very much. That's good. Thank you.
Well, just like to let you know that your talk has inspired me to download a copy of the book, and I will at least begin reading it. So,
okay. Thank you.
Gershom had to leave early, and he said, sadly, I have to go, but thank you for a fascinating talk. And I have a question, but anybody else have a question first? All right. So if you back up to all those different abacus and the Turing machines and all those things, right? So there are connections between these things, but they're not, like you said, they're not isomorphisms. They're compiler more rather than
Not really, because you can think, so what is the programming language of Turing machines? Turing already spelled it out. It's the quintuples.
Right.
What is the programming language of lambda calculus? Well, that would be these lambda expressions, and then the evaluator would be the reduction machine, which would have to be allowed to diverge. So now we can construct a program-closed category from each of these sets of expressions, okay? And a universal Turing machine, any universal Turing machine, would be the program evaluator. Any lambda execution engine would be a program evaluator. So what we have now proved is that we could use padding for each of those to embed them into one another. And it is not too hard to imagine that. So you have the standard, already Turing actually spelled out the standard encoding of lambda calculus in Turing machine. And in Bayern-Direct, we have the other way around. We have, no, we don't. We don't have Turing machines. We have recursive, general recursive functions, and we have Turing machines in recursive functions. So to these reductions, what you would need to add would be the padding. These standard reductions can be blown up to the isomorphisms, believe it or not. They look very crazy, but the padding does the miracle. And then there is, you know, I've been.
But all of these map extremely onto computable functions.
Yes.
Okay, so that's not going to be a program, whatever. That's going to be a surjection. From each one of these goes on to what you call the ether would be the computable functions.
Yes, each of them has the same isomorphically enumerable isomorphically enumerable sequence of programs for each computation, and that for each computation the sequence is enumerable. That would be Myhill's theorem.
Okay.
But you know, the reductions which we are used to can be modified to be isomorphisms using the padding by making each of these, you know, by making untyped lambda calculus into imperative programming language. As crazy as it sounds.
One more question. You mentioned Kolmogorov complexity. It sounds to me like all these different programming paradigms, or all these different types of programs, abacus, lambda calculus, Turing machines, they would all have somehow the same Kolmogorov complexity because they're somehow isomorphic. So there's no redundancy.
No, but that you don't need this narrative to know that. That is clear from so Kolmogorov developed his complexity as the answer to the question, which local function is the entropy integral of? The answer to that question is Kolmogorov complexity. So, you know, the Shannon or Boltzmann entropy. So if people had not pushed Boltzmann down, in principle, from the story about Maxwell demon and entropy, if Boltzmann asked himself which function is like kinetic energy, like temperature is integral of kinetic energy, if Boltzmann asked himself which function is my entropy integral of, he could have discovered the notion of computability without Turing and Hilbert and Gödel and anything. Notion of computability is fully physical. It arises from laws of nature. Boltzmann could have discovered the notion of computability.
Thank you very much. Any other question? Arthur, you had a question.
Well, I was going to ask, is that in your is that explained in your book? Because I can't follow it right now, but if it's in the book, I'll read it there.
About Boltzmann.
Oh no.
Yeah,
no.
Just what you were saying about some of the things you were saying. Yeah.
Well, thank you for asking. Well, this is I have the second volume, which is like half written about complexity, and this is in that second volume. But you know, since I seem to be scaring away that, you know, everyone likes to read from genre which they're familiar with, and if when you write a genre which drops in between computability and categories, then all the readers run away. So I'm not sure that I will be tough enough to finish the second volume. But if I do, then it will be it will be in it. It is written out there somewhere, but it will not be published soon.
Arthur, you have a question? He wrote in the chat that he has a question. Before we close, I just want to, next week we're not meeting anywhere. And May 17th, Arthur Parziganat is talking about inferring the past using category theory to define retrodiction. That means instead of prediction, retrodiction, inferring the past from the present. Anyways, Dusko, it's always a pleasure. Thank you. It was a great talk. It was a great talk. Thank you very much. Ladies and gentlemen, it's a pleasure. Have a wonderful evening. Take care.
Bye.